Let's dig a little bit deeper into CNNs. Again, don't worry about the architecture yet. I'm going to break it apart. The only thing that you need to worry at this point is that your sentence, you can represent it as a matrix. A is your sentence. W is going to give you your filter. You want to multiply your filter by your input sentence, but you cannot do it because they have different dimensions. You pick a window out of A to give you, at least in that window, the same dimension as your W has. And this is the full convolution now. You take W, vectorize it. You take that window of A, vectorize it, do the dot product. And that's going to give you a single number. And then in the previous paper, we decided that we want to pad with zeros. Here, you're not going to do any padding. So your output layer is going to end up having a shorter length compared to your inputs. You add a bias, and then that's going to give you the feature map that you're going to work with in the next layer. And then you're going to have a configuration. Let us start with the input sentence. How do we turn a sentence into a matrix? You do it using vector representations, and you can use word2vec. So now you have a matrix here. Then you need to choose another hyperparameter, and your hyperparameter is what is the size of H. Somebody might say, let your H be 3, let your window size be 4, let it be 5, or you can do them all. And that's exactly what you see here. After this convolution operation, in this case, it's 2, 3, 4 as your window size is, but it could be 3, 4, 5. And then you're taking your sentence and then turning them into different matrices. This is one filter. In this example, you have 2 filters per each window size that you choose, or in the actual architecture that you're going to write, you're going to have 100 of them. And these are basically 100 W's. If you want to put W in a tensor, your W is going to end up have a size of H is 3, for instance. D is the dimension of your word vectors. And then your W is going to have another dimension, and that's going to be 100. Basically, you have 100 of them. You have 100 filters. And this is another way of looking at it, looking at convolutions from this perspective in terms of tensors. Now you're here, you did your convolution. Without nonlinearities, neural networks are going to end up being linear and boring. Therefore, you push them through an activation function, in this case, ReLU. And after you do that, you're going to collapse them into vectors. And these are these C vectors after being pushed, after being activated. These are your C vectors. Then you do a max pooling across the sentence dimension. And this is where you're able to handle sentences of different length, because no matter the dimension that you end up with here, you're going to collapse them into a single number. In this case, after this operation, they're going to end up being 2-dimensional. But here you have 100 of them. You're going to end up with a 100-dimensional vector. Then you concatenate everything together. In the end, you need 2 classes. You're going to multiply this vector by a matrix that takes you from this dimension to 2 dimensions. And then you do your classification. Is the architecture clear? Any questions so far? You also have a dropout layer, and usually your dropout layer is going to end up being where you have fully connected. Why is that? Because convolutions are already parameter efficient. This last layer is going to end up with a lot of parameters, and you want to regularize it. And the L2 norm is just your weight decay. It's the L2 penalty on your weights, not to get too big. And this matrix, you're penalizing its L2 norm when you actually write down the loss function. Now it's time to do a systematic study. As the title says, it's a practitioner guide. And this is where things are going to get really complicated. And what do I mean? In terms of the computation, because it's not only writing your architecture, but you have to train your architecture multiple times for different configurations on different data sets for various initial weight configurations and initializations. And then the question that you're asking is, should I initialize with word vectors and fix them, don't train them again, or should I train them? This is the static word vector version. You are not doing any training on your word vectors anymore, or you are doing non-static word vectors. You free them up so that they are able to be trained. And then the way that you do it, you are going to do 10-fold cross-validation. Basically, you divide your data, your validation data, your actual data into, maybe you keep 10% of them for validation, the rest of them for training. And then you do this multiple times, because it's not enough to prove that one architecture is better than the other, or one choice is better than the other. If you do it only once and train only once, you need to do it multiple times. In this case, 100 replications. And while trying to be fair, you pick everything else to be the same. For instance, the filter region is going to be the same. The feature map is going to be the same. You don't change them. They're constant from one environment to the other one. And then you look at the histogram of your accuracy. Without fine-tuning, you're ending up with lower accuracy. So the entire curve is lower compared to the other one. So the entire distribution is shifted to the left. And this is proof, at least empirically, that you need to do some optimization on your word vector. You need to free them up to be trained. You can do other studies. For instance, you can study your filter region size. What should be the sizes of your filters? Should it be 3? Should it be 5? Should it be 30? And then you can study the size of this 100 here. Why did you choose 100? Why aren't you choosing 200? And you see that on these choices across various data sets, you are going to get different performance, but the ones that are common are the ones that are chosen here. For instance, 100 is chosen here, and 3 or 3 to 5 is chosen here across data sets. I think it's a good time for me to stop. For those of you who have questions, I'll be around.